Okay, hey, welcome. Let's do another online lab, another one on magnetism. I believe this is our third one. So the first one, we had that little compass where we just kind of used the Earth's magnetic field and the monopole thing and how the field fades away. The second one, if you remember, was the charge to mass ratio one. And so now we're on to the one called the Magnetic Field Lab. It's on page 37. There's not a whole lot to really read on this one, but I'm going to say it nonetheless. Turn to page 37 so you can follow along here in the video. But let me kind of explain this lab. This one is kind of the reverse of the last one. The last one I did a lot of talking and really very little data collecting. This is the opposite. This is very little introduction and a lot of data collecting and a lot of graphs to be made. So you're going to have a lot more work on this one than the other ones here. But it's called the Magnetic Field Lab because it looks at we did many different shapes to figure out what the magnetic field is. But if you remember in chapter 30, we learned about some different shapes. And one of the most important one was the solenoid. And so let me begin up here that if you remember doing Ampere's law, we learned that the magnetic field from a solenoid is given by this equation. That is, if you have a solenoid, you're going to get a uniform magnetic field in the solenoid. And so if I try to draw a solenoid, maybe it would look something like this, where the wire comes up, goes over the top and around, and over the top and around, and over the top and around. And maybe I'll just leave it like that. Now, depending on which way you run the current, and maybe I'll just run the current this way in my diagram, and so here's the current I, and so standing over here to the right hand side and looking in, I would see a clockwise direction, and so taking my right hand and curl it, I would get a very strong magnetic field, and I should say uniform magnetic field in the interior parts of this solenoid. And of course Ampere's law can be used to then calculate the infinitely long solenoid, and that's what we would get. And so today's experiment is going to have you build a solenoid. And then once you build it, collect some data on it. And there's three things that this equation is really saying, and so that's why we will run 3 experiments with this solenoid. The first one is this equation is saying that the magnetic field everywhere inside of there is the same value. And so that will be our first experiment. We will take a magnetic probe and we will move it throughout the solenoid. In fact, let me just kind of show you the equipment we will build here in a little bit. This slinky is going to represent our solenoid, and we're going to build it by simply putting one link of the slinky on this side and another on the other side, and then hooking a power supply to both ends. And if we make the current go around in this direction, and so I'll use my right hand rule number 2, then I should get a nice uniform field through it. So we're going to take our probe, and I didn't set up the probe yet, so I probably should have, so I could grab it and show you. But we're going to take the probe, and we're going to measure the field, and we're just going to be able to slide it right inside. And we can move it to different points inside and measure the field. And hopefully what we will get is a nice uniform field inside. And hopefully it'll be something close to this calculation. That's the idea. In fact, we'll even do one step better. We will go to the outside of the solenoid. And so we'll take this probe back over here on the outside, and we'll even put it on this side and use the probe, and we'll see what the field is there. And hopefully we'll get something really small, like a 0. And it'll be nice to see what we really get compared to what our theory, because remember, this is like this ideal solenoid. This ideal solenoid has to be infinitely long, perfectly tightly wound, and of course we don't have that. And so it's really nice to see what we do get. And so we're going to collect data on a real solenoid and then make a graph of our real data, and then also make a graph superimposed upon it of what does it look like in a reality? And so hopefully our first experiment will look something like this. We'll have, say, this magnetic field here, and maybe I'll put position X, where maybe X equals to 0 is the center of the solenoid, and we will probably get a very strong field at its center, and as we go to the left or the right of the center of the solenoid, hopefully we'll see it stay pretty much constant, right? The theory says it should be perfectly constant. It probably won't, but it'll probably get to the edge and drop off pretty quickly. And so I'm suspecting that this is what a real solenoid would look like. And of course, what you're asked to do then is to collect that data and make this plot. So we're going to use graphical analysis or Excel, whichever one you want, and actually plot this. And then, of course, what I want you to also do is then plot the ideal one. And so the ideal plot might look something like that. And so maybe the real one is a little lower than the ideal. It certainly would taper off as you get to the edges a little bit. And then once you get outside, it probably wouldn't exactly go to 0. But this is the idea of experiment number 1. Now, let me talk about experiment number 2. Experiment number 2 is still working with the solenoid. In fact, maybe it would be nice to, let me just check what number 2 is, number of turns in the solenoid. So in number 2, we're going to be changing the number of turns. So remember, little n is the number of turns per length. And so we're going to change the concentration of these turns. And it's going to be pretty easy to do. We could just do this. We could grab the solenoid at some point, and since it's a slinky, just kind of pull it over. And then we have less turns and less turns. And actually, we're going to go the other way around. We will start with something that looks like this. So we'll only have a few turns, and then we will add 3 more turns, take a measurement, add 3 more turns, take a measurement, add 3 more turns, and take a measurement. And then each time we will put our magnetic probe right here in the center of the solenoid and see what we get. And hopefully as the number of turns is increasing, right, that's what this equation is saying, that it's proportional to the number of turns. So your second experiment and then your second graph will hopefully look something like this. Maybe I'll put it down here. We are going to measure the magnetic field based on the number of turns. And we start with, I believe, 18. Let me look down here. Yeah, it says start with 18 turns. Okay, so here is 18. And it says increase them by 3. So we'll go to 21, and then 24, and then 27, and then 30, and 33, and so forth. And we'll run out of turns at about 45. So it says go up to about 45 turns. Okay, and so we will plot our data. And hopefully we will see something that looks a little linear here. And so that'll be our real data. And then also, like I just mentioned for graph number 1, we will also then plot, well, I'm not sure how close they will be, but I'm suspecting that our real solenoid will be a little bit different, but still follow that pattern of an ideal one. And so again, that's the point of this lab, is to help us to understand the solenoid a little better, and the toroid, and the long straight wire. Those are the 3 we're going to be using. So anyways, this would be the second experiment here. And so that's hopefully what you will get. Now, the third experiment is also going to be using the solenoid. Now, again, looking at this equation, you will see that the magnetic field, the strength of the magnetic field, depends upon the current. So in this case, we'll go back to, at that point, we'll have 45 turns here. So we'll just leave it with the 45 turns. We'll have the current hooked up. and we will then get our probe and say, okay, what is the magnetic field when? And we'll start with no current and then continue to go up. And the instructions say start at 0 current and then increase it by 0.3. So we'll go to 0.3, 0.6, 0.9, 1.2, and we'll keep increasing the current. And we'll collect some real data. And hopefully we will see something that looks like this. If we plot the magnetic field versus the current, now again, this equation says it should be proportional to the current, all right? So 0 current should give me a 0 field, and then 0.3 and 0.6 and 0.9 and 1.2 and so forth and so on. And so we will collect some data and hopefully get a measurement that looks like this. That is, what is the field as you change the current. And of course, like all these graphs today, let's put 2 plots on each graph. On this one, we want to plot then, and preferably a different color, although you, in a face-to-face setting, I say, you can put it on your screen in different colors, but when it comes out of the printer, it's going to be gray toned as a different gray tone. And same thing with your PDF. Some of you could do color PDF, I realize, but probably most of you are just going to do a black and white PDF. But I think your converting to PDF will be automatically grayscaled if you just plot it in a different color. But that being said, let me go ahead and then maybe say, well, maybe your theoretical one will be this. But let me say it again, because we're going to do 5 experiments. This is 3 of them, where we're going to collect data of the real thing, and then at the same time, or on the same plot what it should be theoretically. And so we'll kind of look at, okay, what did I actually measure, and then what is the ideal. And so the first 3 are this, working with the solenoid. So let's talk about the other 2. And again, since I need to use this space, I don't really have the camera option unless I go around and back there and move it. So I'll just erase that. Keep that in the back of your mind. But let's go ahead then and talk about the other 2. Now, the other 2 are going to be a toroid. And so this is how we're going to make the toroid. We're going to use this slinky again. I'll move this one out of the way. And we are simply going to put the slinky around some ABS pipe. Maybe you even saw before I hooked it up that the probe, or there's a hole in the ABS pipe here, because here's the probe. And with the probe, and again, this isn't the real probe. I'm going to show you the real probe in a moment here when I hook all this up and start collecting data. But the real probe will look something like this. We're going to start with the probe poked all the way through and all the way into the center part of the toroid, what I often refer to as the donut hole. A toroid is a donut, or for you healthy people, a bagel shape. And so when you put it all the way into the empty part, the donut hole or the bagel hole, when you put it in there, we learned when we did Ampere's law in chapter 30 that the magnetic field should be 0 except for when you're in the tunnel part of the toroid. So in the donut hole part and then on the outside part, the field should be 0. And so we learned this. We learned that the magnetic field from a toroid is the mu naught. I should have put the number of turns first. I like that one first. Okay, so it's the number of turns in the toroid times the mu naught times the I over the 2 pi r. And maybe I'll draw kind of a cross section of a toroid. Okay. And maybe I should even put 0 option. And maybe I even should have done that with the solenoid, because the solenoid was either, you know, the equation we had, or 0 when you're on the outside of it. And I'm trying to say the same thing here. So hopefully in this donut hole part, we will get values of 0 or near 0. And outside of the tunnel part of the toroid, we will also get 0. Because the toroid is a really nice shape to make very, very strong fields. In fact, the toroid usually makes fields stronger than the solenoid. In fact, you can think of a toroid as exactly that. It's a solenoid, and instead of having the field kind of leak out, you put it back on itself. And so you get 0 fields a little bit better outside than this ideal solenoid here. And this right here is the equation. And so if the current runs something like this, current runs over the top, and then around underneath, then over the top, then down underneath, and then over the top. If I take my right hand and curl it, I would get a magnetic field that from this cross-sectional area would be pointing in a clockwise direction. And let me put one more little tighter in there. Because what this equation is also saying, and so this is kind of the bad part of a toroid, of course depends what you want, and a lot of times we do want strong and uniform magnetic fields, and this is saying you will not get a uniform magnetic field. You will get it strongest where R is the smallest. Now, let me emphasize, R is measured from the center of the donut hole. So you would have what I might call an inner radius, and then the final one, an outer radius. So I don't want you to think that R is measured from this edge, otherwise you might say the field goes to infinity. And that's not what the math said. That is not the way we did the Ampean loop to figure out what the equation is for the magnetic field inside of our toroid. And so we're going to build this, and we're going to test this idea. That's the whole idea of today's experiment, is to test this. And so you're going to collect, let's see, what is it? It says here, measure and plot the magnetic field as a function of position. Okay, so let's call the 0, or as close as we can get. And so if I come back to our equipment, you'll see that if this is the magnetic probe, I'll push it all the way through. And the closest I can get, I think, is about 1 centimeter. We'll measure it with a little more accuracy in a little bit here. And so my smallest R would be 1 centimeter. But I'm at the inside, the donut hole part. And then we'll keep moving out. And then it says, how far do we move at a time? A half a centimeter. So we'll move a half a centimeter. So we'll take a few measurements while we're still inside of the donut hole. Then finally we get inside the interior part of the donut. And then eventually we will move out and get outside of the whole donut. And so we will have collected data that would look, I guess, in a chart, something like this, the magnetic field as a function of different positions. And so your job is going to be to make a plot of the magnetic field. And hopefully you'll see something that looks a little bit like this, that when you put the probe as close as we can, we get a field that is almost 0. But if we take an inner radius and an outer radius, our first couple of measurements will probably be pretty small. And maybe not exactly 0, but hopefully something close to that, so we can kind of get a feel for what we're trying to say here, is that the magnetic field inside the donut hole is 0. But then once you take the magnetic probe and you cross that boundary, you pull it back and you actually get your first measurement that is inside of the interior part of the donut, hopefully it will shoot way up to here. And that then means our equation would go from 0 magnetic field to this equation with the smallest value of R we can have and still be inside of the interior parts of our donut. And so it shoots up. And then as you make a few more measurements moving out, you can see that this is saying it has a 1 over r squared value. So it has that famous shape, the hyperbola, as it angles down here. Maybe I shouldn't say angle, but as it tapers down, it should follow a hyperbola. And so hopefully we'll see that. And then, of course, at some point we will make our measurement and we will then finally get outside of the donut. And that's where hopefully it will drop quickly and taper off. And of course, like the other ones I was mentioning, your job is then to plot what did we actually measure versus the ideal. And so do the ideal in a different color. I've been doing red, so I'll stick to that. And the ideal says, well, it's 0 when you are either in the donut hole part or when you're outside the donut hole part. Okay. But when you're in the interior part, it follows this equation, which has this 1 over r pattern to it. So right at the radius, it would shoot up to some huge value. And then it would have a hyperbola shape to it, and then instantaneously drop to 0 again. And so, like the other 3 I was mentioning, here is plot number 4. And again, put both plots on it. The magnetic field that you actually measure and the magnetic field that is idealized. And so that's plot number 4. And it should look a little bit like that. And then let me talk about the final plot you are going to do, which is plot number 5. And that's just take a long straight wire. I didn't grab one. Let me grab one now. But I will show you that I'm going to just take a wire and just kind of hold it and take my magnetic probe here, and I'm going to start real close to it and just move further and further and further and further and further and further out. Because this also was one of our common shapes, and we had this equation. The magnetic field looked like this. It looks really like the same equation. However, I guess we have a little different meaning to it, because if this is the wire carrying the current up in this direction, then using my right hand, the magnetic field, so right hand, grab it, thumb in the direction of the current. So what I call right hand rule number 2, right? My right hand rule number 2, again, you look for what is matching the shape of the current. If you remember over here with the toroid, my fingers matched the current, so I did here, and that worked also for the solenoid. But the other thing with right hand rule number 2 is look for what matches, and my thumb is straight, which matches the wire. So okay, my thumb will be the current, so my fingers will be the field, and so I will get a field that will look like circles around it. And I'm not sure my picture illustrates it well enough, but the lines should be closer together where the field is strong, and according to this equation, it should be strong near the wire itself. And so that's the experiment we want to test. We want to collect some data. And once we collect that data, we then want to make a plot. And just to make sure it stays on the video camera, I'll put the plot right here. And so we want to plot the magnetic field as a function of position. And so this equation, a lot like the toroid one, although the toroid, this was only valid inside and R was measured from the center of the donut hole part. Here the R is measured from the center of the wire. So the closest I can get will be something like a half a centimeter or maybe a centimeter. Let's see when we actually make the measurement. But this would be my first measurement of the magnetic field. And then as I move away, it should follow the shape of a hyperbola. There is no zero. And we don't have to go very far before we can't measure anything more, or to say a different way, we get overwhelmed and by the background magnetic field, the Earth's magnetic field and the rebar in here, because this field is just not that strong. In fact, you can see the difference in this equation versus this equation. This one, and the number of turns can be many times. And my little toroid here has about 40 to 50 turns. We'll count them. And so the field is 40 to 50 times bigger for the toroid than it is for the straight wire. Although I must say, for the straight wire, I can get a little closer with my R than I can here, because this is only valid to the inner part of the smallest R, what I call the inner radius. Whereas this is valid all the way up to the edge of the wire, and the wire is much thinner here. So we'll be able to measure the field at the beginning, but we don't have to go really far before this tapers off. And that's why on this one I'll crank the current up as high as our equipment can go, and which isn't that high. You'll see it's like 5.2 amps. But like our other ones, let's do this. Let's also on the same plot, so this is your fifth and final plot, let's plot then the idealized one. And so on this plot too, hopefully you will have the one we actually measured and the ideal one. And so it gives us hopefully a chance to kind of make that important discovery here that what we talk about on the textbook, these idealized, doesn't really always match reality. And that's why, you know, building a test model, that's why laboratory experiments, you know, so in science, a laboratory experiment, and in engineering, a test model are so crucial because you build it, and things aren't exactly perfect. You build it based on perfection, and you use these fields. So if I'm building a microprocessor, a lot of times I will, you know, set these up with the calculation of these ideal fields. And so maybe you get all your design done, and you say, hey, this microprocessor should be able to operate at 4 gigahertz. Before I get interference, before things get too fast and they interfere with themselves, how the magnetic field of one transistor affects the transistor at the other one. And then you actually build it and you realize, well, wait a minute, as I test it, I don't really get that high. You know, maybe I only get to 2.5 gigahertz. And then things start fouling up. Hey, but at least I got a processor to 2.5, and so maybe that's good, or maybe I'll tweak it a little more with another test model before we go into production. And so we need to know exactly what's going on in an ideal world, and then say, okay, what happens in the real world? And you see that really well. And so that's why I want you to do all 5 of these plots. Plot what we actually measure. And you'll see we're off of the ideal world because, you know, like the solenoid, we're not making an infinitely long solenoid. It's impossible. So let's see what we actually measure and compare it to this ideal solenoid. Again, the toroid is not infinitely tight, so let's see what we measure and compare it to this perfect theory. Okay, and then, of course, the long wire. All right, well, with that said, then we'll jump over. Let's start our measurements. Hey, welcome. Let's collect our data now. Okay, so we talked about all the theory behind it, and so now I've hooked up the equipment and got the probe out here. And so let me just show you, if you remember last time I was kind of playing with this pen thinking it was the probe. They don't look that much different. But this is the probe. There's a little white dot, and the idea is to get the magnetic field to go perpendicular to the plane of the white dot. And sadly then, with only one set of hands it's going to be difficult to get accurate measurements, but I'm confident we can get at least accurately enough that you'll see the pattern. Because in a classroom setting, I would show how you can hold it with one hand, because if you just do a slight rotation with it, you get a slightly different angle. And so you want to keep that angle the same the whole time. And then you need to be able to write that down. So I'm going to try to do both. So I'm going to hold it with my right hand, which my left hand is my dominant hand, so I can write, and then try to keep that angle the same for each of my measurements. And I'm going to try to get it back to the same value that I calibrated when I turned it on here. And so we'll just see what happens. But I am pretty sure we'll get a good enough data here. Let's see what happens. I'll just kind of make myself a little chart. Here's position, and here is field. And I don't know if you can kind of see just the edge of the monitor right here, but this probe goes down and plugs in, and so there's a screen right there that is telling me the strength of the magnetic field. And this power supply is set at 2.5 amps with current running through it. And so let me begin right at the center of the solenoid. And I should get a reading here of something close to a 0.3 millitesla. But let me begin here. All right, so at position x equals to 0, and I'll put this on the board, I get a reading of 0.275, and that's in units of millitesla. Let me move over a half a centimeter, and I get a reading of 0.272. Let me move another half a millimeter, and it looks like I get a reading of 0.264. Let me move over another half, and it looks like 0.260. Let me move over another half, 0.240. All right, now still inside but barely, another half, 2.211. Oops, and at 3.0. Oh, now I'm starting to get outside. 0.154. At 3.5. 0.030. At 4.0, now I'm on the outside. 4.0. I get a reading of 0. Nice. At 4.5, I get another reading of 0. And at 5.0, I get a reading, it's actually a little negative point. And it looks like a 0.12. And I guess, whoops, I moved it. Maybe I'll do one more. So I'm at 5.5. And that's a negative 0.0, let me call it 13. Okay. Oh, that kind of hurt the back. Maybe I'll lower my legs here. Whoops. Don't go to sleep on me. All right. Now, if I go the other direction, let me call it a negative 0.5. So let's see if I can get it back into that same spot. Here's about 0. Oh, good. Same number. 275. Okay. So let me go 0.5 centimeter this way. And I get a 0.272. Let me go negative 1 centimeter. 63. So 0.263. Negative 1.5 would be 264.264. Negative 2.0. These are in centimeters, of course. 0.264 again. Negative 2.5 would be right about there. 263. Negative 3.0. 262. Negative 3.5. Might be a little tricky here. It's starting to get out. How about 240.240, and then negative 4.0, 0.126, negative 4.5, 0.0, was that 00? Whoa, try that again. 4.5 would be right there, 4.5. Let's call it 0.025. Negative 5.0 would be right there. Let's call that a 0. And one more, negative 5.5. And let's call that a 0 also. Ouch. My back. So I told you that this lab was a lot more about collecting a lot of data and then making our plots. Let me transfer these numbers onto the board so you can maybe see them a little better. But here then is what I have. Here's the magnetic field and here's the position. Let's go from a negative 5.5, negative 5.0, negative 4.5, negative 4.0, negative 3.5, negative 3.0, negative 2.5, negative 2.0, negative 1.5, and go again here. Negative 1.0, negative 1/2, 0.5, 1.0, 1.5, 2.0, 2.5, 3.0. Should I squeeze it in here? Now, 3.5, 4.0, 4.5, and 5.5. So what is the magnetic field at each of these locations? And so looks like I got a 0 and then a 0. The 4.5 was 0.025. The 4.0 was 0.126. The 3.5 was 0.240. The 3 or negative 3 was the 0.262. The 2.5 was 0.263. The 2.0 should be 0.264. And negative 1.5 was 0.264, negative 1 was 0.263, negative a half was 0.272, 0 was 0.275, 1 half was 0.272, 1 is 0.264, 1.5 is 0.260, 2.0 is 0.240, 2.5 is 0.211, 3 is 0.14 or 154, 3 and a half is 0.030, 4 got a 0, 4 and a half got a 0, oh I skipped 5 and then 5.5. And then 5 is actually a negative 0.012, oh that's pretty close to 0. That's probably just more of the uncertainty of it, and then a negative 0.013. So let me say, like I said at the beginning here, before I started collecting the data, is you go ahead and enter these into a graphical analysis. And hopefully you'll get something that looks like this. You will have a plot that looks like it has its largest value right here at the center of the solenoid. And it looks like it tapers off and then really drops off quickly, and so maybe you'll get a graph that looks something like this. But also do the theoretical one. Now, when I say the theoretical one, what I mean is get out your calculator and calculate this theoretical value. That is supposed to be the magnetic field at its center, and then 0 when you're not at its center. So what I need to give you is a couple of pieces of information so you can do this. And the first of all is the radius of this. And the radius of this in centimeters is about, let me just check here, about a 3.7, okay? So at negative, let's call this negative 3.7, which you're going to plot every increment, so I guess between negative 3.5 and negative 4.0, and same thing over here, between a positive 3.5 and a positive 4.0, it should change. You should get this value, and so you're going to get this nice straight line out to here. And then from here forward, you should get 0. Because these are our two equations for the magnetic field from the solenoid, as I was trying to say a few moments ago. And so hopefully your graph and your computer will kind of slope it together like that. And so you'll have this red one, or grayscale it, that is the theoretical one, and then you'll have this one that we actually measure. Now again, let me give you a couple more numbers you're going to need, besides knowing what the radius is, so you know when to apply a 0 field and when you apply this field. This field, remember the N is the number of turns per length, okay? And so I have counted 48. Yes, 48. And so that number here is 48. I also measured its length before we started. I used this meter stick over here. But the length of the solenoid is a ½ a meter. And so this is 0.5. And the current, I think you can see here on the dial here, it's 2.5. Maybe I'll walk around this side and kind of get next to the camera here. Yeah, so you can actually see that number, but I'll write it anyways. The current here is 2.5 amps. Okay. In fact, let me let it cool down a little bit while I'm getting ready here for experiment number 2. But your job, I'll say it again, is to get out your calculator and get the theoretical value. Now let me give you a help on plotting these. Again, I don't care which program you use, but I think graphical analysis is, just because it's user-friendly, is a good way to go. But here's where you want to be careful. Usually, and well, I'll say the first plot, the plot that's our measures are really easy. Just take the first column, the x-axis, and type in x, and make the next column, which is y, and just change it to b, and type in your values, and then do connect the dots, and you'll get your first graph. But for the theoretical one, you might be tempted to make a new calculated column, and don't. Because when you have what in math we call a piecewise equation, in other words, you want this equation applied when you are under 3.5 from the center, and you want this equation applied when you're greater than 3.5 or 3.7. And there's no way to do that. So I would just encourage you just to type it in. And so when you make that third column, call it a manual column and just type it in, because this is going to be the same number. And so for all of these points, which would fit in this category, from a positive 3.5 down to a negative 3.5. For all of those, just type in the number that you calculate and watch your units, because if you stick to the standard SI units here, you're going to calculate this in Tesla. And please know that I have measured everything up here in millitesla, okay? And so whatever number you calculate here for that theoretical one, then take it and multiply it by 1,000. So it will now be in unit of millitesla. And so again, that third column would be you just put in a solid number. Let's just say the number comes out to be, and it probably comes out to be something very close to this. Let's just say it's no, actually it's going to be a little lower than that, because like I said, we always measure a little lower than the ideal one. In fact, memory, I actually, now that I think about it, I think I remember doing these calculations last year, and it comes out to be 0.3. Okay, so you're just going to type in 0.3, 0.3, 0.3, 0.3, 0.3, 0.3, 0.3, 0.3, 0.3, and so you'll see this 0.3 across the top here. And so you should be getting something like this, 0.3, like that, and then kind of a top hat type of a graph here. And then of course on the other ones you'd be typing 0, 0, 0, 0. So you have the red one and then the black one. And so I'll say it again, all 5 of these are designed to, let's measure the real thing and then compare it to the theoretical value. And you'll see that they'll be close, not perfect. In fact, I would say even reasonably off perfection, because again, infinitely long solenoid, infinitely tight wrap, we don't have either of those. And so we are weaker than that. And we don't have this perfect shut-off between inside and outside. And so we kind of hopefully will see this kind of crown shape, and it's lower and then off to the side. Okay, so that's the first one, and maybe the hardest one. All right, so now let me clear this off a little bit and get to the second one. And as you probably recall me saying, our 5 experiments, the first 3 are using this solenoid. So I'm going to go into the second one. And the second one, I think I can probably turn around here on the board. This one says vary the number of turns, but don't change the current. All right, so I will leave the current set at the 2.5 amps, and I'll set up a little table here. And so it is change the number of turns in your solenoid here. Yeah, so I have 48. I don't think we are asked to go that high. We're asked to start at 18 and measure the field. And then go up by 3s, so 24, 27, 30, 33, 36, 39. Number of turns, field. Okay, 39, 42, and 45. Oh, I probably could have squeezed that in there. All right, and so let's measure the field. Now again, when we go to compare it to the theoretical one, remember I'm measuring in milliteslas. That's what my equipment is set up. And you can't see it, but it's got a big sign that says measured in millatesla. All right, so I'm going to change things a little bit. In particular, remove this ruler. There's no need anymore to measure the distance across it. We're going to just always measure the center of the solenoid, and I already showed you the length of it is a ½ meter, so we'll get rid of that. But here's my electrical wire, and I will show you something kind of nice about this equipment. I have it set up to be on a constant current. So no matter where I hook it up, and so now we're going from here across here, I'm going to get to 2.5 amps. There's less resistance because there's less wire. And so the computer on here adjusts the voltage accordingly so that I get the 2.5 amps. So that's a nice little design here of these power supplies here. We can set them for a constant current source. And so see, 2.5, even though I'm going a shorter distance and less resistance. So that will become useful because here's what I'm going to do. I'm going to get 18 loops to start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And make sure the solenoid stays the same length. I'm going to pull it to its end here. And then if I just clamp on, I have only 18 turns over this ½ meter, and I can now get the field. And I hope I won't change things too much if I come in from the other direction here. But let me try to come back each time and hold it at exactly the same position and the same angle as I turn around and write on the board. And so right now it looks like I've got a point, I'll call it 118. And so 0.118 there. Let me then disconnect and go 3 more turns. 1, 2, 3. Oops, don't come apart. And let it go. And hook it up. Okay. And then now I have 21 turns. And let's see if I can kind of hold it in the same spot. And hopefully I'll get you some decent data here. But it looks like I've got a 0.130. 0.130. Good, so it went up. Let's go to 24. Okay, so 1, 2, 3. And so I'll go 3 more turns here. And find the center spot. And hopefully have it set up the same angle. 0.155. 0.155. All right. Let me go 3 more. 1, 2, 3. And see if I can hold it in the same spot. Okay, that looks like about it. And I get, went to sleep here. And it looks like 0.189. 0.189. Okay, let's do another 3. 1, 2, 3. Okay. And let's see, that looks like about the center there. Hold it in the same spot, and it looks like I am at 0.197. 0.197. Okay. Disconnect. 1, 2, 3. Yeah, it was an interesting set of steps there. But let's see what I get here. All right, so let's put it in here. And I get a 0.209. Okay, 0.209. All right, let's go 3 more. 1, 2, and 3. And I guess I should keep looking here. Does that keep going back to 2.5 amps? Good. And hold it kind of in the center there. Okay. Hopefully the same rotational angle. 0.244. 0.244. Let's do another 3. 1, 2, 3. And pick it up. 2.5 amps. Find the middle again. Maybe right about there. Okay. Looks like 0.268. 0.268. And looks like we got 2 more to do. And 1, 2, and 3. Hold it in here, hopefully. At about the same angle. And I got a 286. 0.286. And then finally, and I actually like those numbers better. I think they're closer to the theoretical one. I didn't even get that high a moment ago on the first one when I had 48 turns or 45 turns. 1, 2, and 3. So maybe I didn't hold the angle right. One of the things that I emphasize when we're face to face is, have somebody hold it and don't let go. They always want to keep that same rotation. But I have to keep adjusting it myself here. But let's finish off here at 0.302. And like I said, I think that's what it calculates out to be in the theoretical. Oh, good. So maybe this data is a little nicer than the first one. But again, as I said, it's not so much on the perfection of this particular data, but to see and learn a little bit more about the solenoid, the toroid, and the long straight wire, as well as see how a theoretical and an experimental are close. All right, now I'll talk about this one again, but you are to go to graphical analysis and make a plot of the magnetic field, the N value. And the first thing to do is just to put in, your N values and then these magnetic fields. And then, of course, do a regression line, and you'll get something that looks like that. But also, make a new column, and so a new column for B, And on this one is where I would say go ahead and make a new column. And in this case, do a calculated column. I suppose you could also calculate them by hand and then type them in. So either one would work. But on this case, we only have one formula. It wasn't like the first case where we had a 0 on the outside and some other number on the inside that was a constant. It just didn't make sense to have a formula for that one. But this one does. And so if you enter then this formula, and let me remind you also to multiply it by 1,000, because you will probably put in the 4 pi times 10 to the minus 7. You will probably do a 1/2 meter for here. You will probably do the 2.5 amps for here. And then when you put a formula, you would then say times this column. This is the end. But if that's all you do, you're in Teslas, and you want to compare it to milliteslas. So make sure then you, in that calculated column, you multiply by 1,000. Otherwise, you'll see this theoretical one 1,000 times lower than this one, and that could be confusing to you. And say, hey, they don't compare, but they will compare. And so go ahead then and put that in there, and hopefully you'll get something that is nearly the same. And so this would be your second graph. And I'll say it again: your graph, all of your 5 graphs should have 2 plots on them. The one we actually measured, and then the theoretical one here. Okay? And so that'll be your second graph. All right. Let me turn this off so it can kind of cool down here. Let me again do one more of the solenoid here before I change the equipment out to the toroid and set it up. And this one says change the current. All right, so I'm going to make a little chart here that says, all right, what would happen if I were to change the currents and measure the magnetic field, starting at 0 amps, and again we'll be measuring in millitesla, and go to 0.3, 0.6, 0.9, 1.2, 1.5. Should I try to squeeze it in here? Yeah, 1.8, 2.1, and 2.4. And so let's try all of these currents and see what kind of field we get. We will leave the number of turns here at the 45, and that way we have something we can compare in our calculation. So I just did it at 45, and of course if I turn it on, this should turn the current all the way up to the 2.5 that we were using. And so I will begin by taking and turning both dials for current all the way down, and get then 0 currents. I will try to hold my probe in here the same way. And this is probably where I get some imperfections, but I do get a negative 0.01, which is probably pretty close to a 0, but let me write what I actually measured. So negative 0.010, there's my first reading. So I will turn up the constant current source, and I don't know if this fine adjustment will go far enough. Doesn't look like it, so let me go with the coarse one here. And get it to 0.3, okay? And so at 0.3, I will try to hold it the same way. And I get don't go to sleep on me. I will get 0.031. So 0.031. Let me turn up the dial to 0.6. And try to hold the probe in the same angle. and get 0.070. 0.070. Nice. All right, turning it up again to 0.9. We do the fine adjustments. So there's 0.9. And hopefully holding it in the center and in the same angle, and 0.107. Turning up the current again to 1.2. And I get 0.144. And then turning it up to, let's see, put the fine adjustment in the middle here, okay. 1.5. Okay. And I get a 1.76, or 0.176, excuse me. Let me go up to 1.8. And get 0.215. And 2.1. And I get 0.252. And then finally, our last one here at 2.4 amps. It's getting warm at all? No, not really. And I get a 0.288. 89, 0.289. Ta-da! All right, so this is our third and our last one of our solenoid. Then we'll switch over to the toroid and the long wire. But let me just make that same comment that your job now is to take that numbers and go to graphical analysis and plot the magnetic field versus the current. And the first thing is to just put current on the x-axis and put the magnetic field on the y-axis, and hopefully you'll get something that looks a little bit like this. And so do a linear regression line and say, okay, there is the proof that it changes linearly with the current. And then, of course, make a new column, and so this will be the theoretical value, new column. And in this case, too, I would say you can go ahead and do a formula. So go new, go to the data and go new column, and it'll be a new calculated column. And you can then just put in this formula, the mu naught, the little n, and the I, reminding you that the little n is the number of turns over the length times I. So your formula is then going to be the mu naught, and then the number of turns is the 45. The length is a ½ meter, and then it would be times this first column, which is times the current. Let me also remind you again that you need to multiply that by 1,000, because if you do this 4 pi times 10 to the negative 17 for the permeability of free space, then times the current, which is in amps, this is all going to come out to be by itself in Tesla. So you need to multiply by 1,000 to make it milliteslas, so you can compare it with our probe, which measures in milliteslas. All right, but hopefully then you'll get something that looks like that. So that's 3 of the 5. Well, let me switch over now and go to the toroid. Okay, hey, well, welcome back here. I switched out the equipment and played a little bit with it. And looks like my computer went to sleep also on me. was sort of happy with it. So this is the best I'm going to get. I really wish now I had a cameraman. This would be great to zoom in. I changed the angle of the camera just a little bit because in order to hook up the wires just right, I needed to put it over here because this is the opening, and I need to cancel off the Earth's magnetic field, and so I've done it in kind of a direction that I have to move kind of in a north-south. And so without the chance to zoom in, I'm hoping you can kind of see that I do have a toroid. I do have my wires hooked up. If I can even turn it on, I was playing with it and I adjusted it to 2 amps, and so that's what the procedures say. They say set up the toroid, and again, set it for 2 amps, because if we go to the 2.5 like we've been doing, remember the toroid tends to be stronger than the solenoid, and we go beyond the capabilities of our magnetic probe, and so we don't want to go anything above 0.4. Even 0.38 is really kind of pushing our probe the way it's been calibrated and set up. So I didn't want to do that, and so that's why the current is set up. Now I'm going to make a little change. The author says put the probe all the way to the center. Well, I can't do that. I can't go to 0. The closest I can get is 1 centimeter, and I don't know if you can see without the zooming in, but I've put a little plastic ruler underneath here so that I could take my probe and start with it all the way in. And you can't see from your angle, but as I look down here, the closest I can get that little white probe is at 1 centimeter. So that's where I'm going to start. I'm going to start at 1 centimeter and move out. And I'll just try to get them on this piece of paper here if I can, and then we'll transfer them on the board and talk about the graphs for a moment. And I'll just do my best to try to hold it at the same level and the same angle, and it's just not as easy with one set of hands here, and probably not easy for you to see it without the zoom here. But I'll just move it out. I will say that we start to enter the interior part of the toroid. Probably 5 is a good way to say we're completely in, yeah, and 4 we're just getting on the inner boundary of this plastic piece that makes our donut hole for our toroid. So I'd say 4 we're not in, and 5 we are in. And so that's why I decided to change it. And even though the instructions say every ½ centimeter, I go, well, let's just go every 1 centimeter. So I'm going to go from 1 to 15 centimeters and have 15 pieces of data instead of 30 pieces of data, only because my accuracy was really hard, and as I was playing with it, it was just a little too long and a little too awkward for me. So that's how we'll collect the data this time here. Okay, so with that in mind, let me go ahead and begin experiment number 4 here. All right, and so I'm going to maybe adjust this, look over the top. Looks like I've got the right angle. Whoops, don't want to push it too hard. Looks like I'm at 1 centimeter. I'll look at my field probe, and it says 0.02, okay? Move it back 1 centimeter till I'm over the 2 centimeter on the ruler, and it says 0.024, 0.024, okay? Then I'll move it over the 3 centimeter, and it says 0.032. 0.032. So I'm getting some kind of field and some kind of variation as I get close, but it's pretty small still. I'll put it at the 4 centimeter here, and this says 0.06. 0.060. Okay, now hopefully I'm going to see a real big change. Where's the 5 centimeter? Because when I'm at the 5 centimeter, I get, yeah, 0.340. No, wait. Let's call it 370. 0.370. Let me go right over the 6. Call it a 0.322. 0.322. Let me get right over the 7 and call it a 272. 0.272. Let me get right over the 8. How about 235? 235. Oh, good. So it's dropping down. I'm still in the interior part of the toroid. Here is the 9.209. 0.209. Here's the 10, again, still inside of the interior part of the toroid. 0.182. 0.182. And then 11 centimeters. Okay, we're right at the boundary. I guess I might say we're still inside. .153. But now I'm outside, but although barely. 0.018. Wow, a big change. 0.18. Good. And that's really what I would have liked to have seen. A big change once we get outside the toroid. 13.004. 14. 004 again. 15, last one. I'm going to call it a 005. And I'm not exactly going to say it's gone up, but those are really, really small here. All right, let me transfer these onto the board so you can enter them into your graphical analysis for your fourth graph. And so here's what I have. I have, and I changed the angle of the camera, so why don't I put the data table right over here. Still see that? Okay. So if this is the R, I've got in centimeters. 1.0, 2.0, 3.0, 4.0, 5.0, 6.0, 7.0, 8.0, 9.0, 10.0, 11.0, or I should say 0, 12, 13, 14, and 15. And so what did I measure for the magnetic field? Again, in millitesla. And I got a 0.02, then a 0.024, then a 0.032, then a 0.060, and then at 5 really shot up. Good. Because that's where we went from the donut hole to the interior part of the toroid, and that's what I want you to see. And then it tapers off because, again, of that equation. Well, we should talk about it here. Okay, so 6. So at 6, it's 0.322. 7 is 272. 8 is 235. 9 is 209. 10 is 0.182, 11 is 0.153, 12 is then getting to the outside, and look at it just drop off, 0.18. So good. Outside the interior, both in the donut hole and outside, it's getting close to 0. Ideally, it would be 0. 13 was 0.004, 0.004, and 0.005. So all this stuff is outside, and all this stuff here is inside of the donut hole. And so we've got a nice decaying pattern. It kind of looks like it is going to be one of those hyperbolas inside of the interior part of the toroid, and then zeros when you're either completely outside or completely inside the donut hole. But I'll say it again, so here's what you need to do. Put those into graphical analysis and plot the magnetic field versus the radius. And so again, hopefully you're seeing some low numbers, 1, 2, 3, 4 low numbers over here. Maybe a little bit of increasing, then a huge jump up, dropping off, then a huge fall. And if you connect the dots on graphical analysis, you should get something that looks a little bit like this. And that matches what we've been talking about in class, the theory behind this. The theory was that for a toroid, you get a magnetic field of 0 when you are either in the donut hole part, so that should be here, or on the outside part, and so starting at the 12 centimeters. I should have pointed out that the inner radius is about a 4.5, and the outer radius is about 11.5. Let me just kind of double check that. Yeah. And so from 11 to 12, we've done the transition from inside to outside. And of course, the other equation for the toroid is what do we get when we're inside the interior part of this, and that is the number of turns mu naught times I over 2 pi r. And that is a equation that looks a little bit like that. So just like on the other three, this fourth one, you are to plot what we actually measure and then the theoretical one and show them both. That way, again, hopefully you'll begin to understand what we mean by these theoretical ones, but also tie in that they're not, perfect. And this is what we actually get when we build a solenoid, at least like this. And in this case, you're going to need to know how many turns you have. Now, let me give you a helpful hint on plotting the theoretical one. Again, I would not make a new calculated column. It's difficult, if not impossible. I don't know how you do it in graphical analysis. You can't put a piecewise equation. When they say make a new column and calculate it, they just calculate the whole thing. They don't say, well, only calculate it in this range. And that's too bad, because if we could do that, then we would want a calculated one from about 5 to 11, but then we would want constants of zeros theoretically for the other places. But graphical analysis can't do that. There is no conditional option like there is in Excel. So if you want to do Excel, you could say, well, if, and then you could say something, if R is less than 5 or greater than or equal to 12, put 0. Otherwise, use this formula. So if you wanted to do a conditional formula in Excel, and I would assume Google Sheets, I'm not as familiar with it, has the same conditional options, you could put this as a calculated column. But I think that's too much, and I don't want you to learn any more software. So I'm going to suggest this. In graphical analysis, just make a new, and call it a manual column. And then first just type in 0, 0, for these positions. Maybe I'll show you kind of a new column here, new column. Just type in 0, 0, 0, 0 for those. And this new column here, type in 0, 0, 0, 0 for those. Now, these other ones, you're probably going to have to just get out your calculator and put it into this formula, because the R keeps changing, and type it in because we're in a manual setting. So let me point out that the number of turns is the 48. That's, I didn't count it for you, but before I turned on the camera, I did count them. And I used the whole slinky, and the slinky has 48 of them, as we got started with. So that number is 48. You know mu naught. The current, as you saw, would be the 2 amps here. So use the 2 amps. And then, of course, the radius. And, of course, be careful with your units, because these R's are in centimeters. So make sure, like the first one, you put a 0.05 in terms of meters. And then also remember that calculation would give you the field in Tesla. So you also need to multiply by 1,000, and that's what you would type in right here. And so just do the same thing for 6, and for 7, and for 8, and for 9, and for 10, and then 11. So I would hand calculate those 7 and then just type them in instead of trying to learn something new in Excel. Although unless you want to challenge yourself, that's fine too. But graphical analysis, as far as I know, doesn't have anything that would give me that option. But I'll say it again. your graph number 4 should look a lot like this. So told you we were collecting a lot of data today. So a lot of data, a lot of graphs, but hopefully giving us a better understanding of the toroid and the other 3, which were the solenoid. Now we'll switch over and do the long wire. So I'll have to change this equipment out and do some testing, and then we'll come back and do the long wire. Okay, now we're ready. We're ready for the last one. This is number 5 of 5. And now let's measure the magnetic field from a long wire. And this one's pretty tricky. I have been playing with different things, and it would be nice again to have a lab partner with the extra set of hands. That's normally how we will do it. But I think I can get it kind of trapped into these blocks and then kind of let go and maybe get it back in the same position. So let's give it a try. Let me show you what I've got here. I've got the magnetic probe still, and so I can look on the screen here and get the value of the magnetic field. But what I've done is I've run the wire from the power supply behind the blocks, and it's coming up and then going over the top of the block. And so this will be my long straight wire. I know it's not really that long, but in a face-to-face setting, I usually have one student hold it something like this, and the person just kind of holds it. And we've got quite a bit of wire, so they make it much longer. But I think this is going to work fine. I was playing with some values, and they were looking really good. And then I'll just write down, and it says to put as much current as you can with this little power supply. And so 5 amps is where it tops out at. And so you'll see when I turn it back on, it should go back to the 5 amps that I was playing with here. And then I'm just going to take this probe, and I got the 2 levels of blocks, so I can put the ruler in here, so I can just hold it at the right angle and then go along that east to west line and start moving it back every half a centimeter and see what the field strength is. And so I think you could see that. I tried to get it right angle there with the camera. Didn't change the angle from the last time, so we're a little bit towards this side. Let me just turn it on then and show you what I mean here. So I'll turn it on, and yeah, sure enough, it goes to 5 amps, which of course it only needs 0.6 volts to do that. And so the current comes out, goes under the block, and is coming up. No, excuse me, I said that wrong. It's going over the top of the block. Yeah. And so if I took my right hand and pointed my thumb down and grabbed the wire and turned it, the field would, on this side, be coming out towards you, just like it was in the solenoid and the toroid. Okay, so I'll make my first measurement. I'll kind of hold the wire kind of in this position straight up. About the closest my white dot can get is about a half a centimeter here. So I'm going to take my first measurement. It's actually a hair more than a half a centimeter, but I'm going to call it a half a centimeter. And whoops, let me wake up the computer there. All right, and so let me put it at a close as I can get it anyways, and see what I get. Oops. Okay. There we go. Like that angle better. That just seemed a little bit low. I didn't quite have the angle right. Okay. So let's call this our first measurement, 0.112. Okay, so 0.112. That's at a half a centimeter. All right. Now, if I can get it back to the same location, let's go 1 centimeter. So 0.6065. 0.065. And again, let's see if I can get it back, or at least something close here. Let me go to 1.5 centimeters. And 0.042. 0.042. Now let's go 2 centimeters away. 0.02, well, yeah, let's call it 2, yeah, 30. 0.030. Okay. Let's go 2.5 centimeters. 0.021. 0.021. Okay, let's go 3 centimeters. 0.015. 0.015. All right, let's go 3.5 centimeters. 3.5. Let's call it 0.010. 0.010. Why not? That was 3.5. All right, so let's go 4. 4 would be right here. And I know in the past we really haven't got anything of value beyond 5 centimeters. 0.0, well, that's a 6? Sure. 0.06. 0.060. I think I meant 0.06. Let me try that again. We're at 4. Yeah, 0.006. That'd make more sense. And we might be at about the best we could do. I'll try 4.5. 0.05. Just jumping around like, I don't know if anything is really significant or of value. It's probably much more sensitive to my slight touches and my hang-ups here. So we'll do one more, but I'm not sure these last ones are even worth plotting. We'll have to kind of let you decide to see if that's anything worth measuring. Go 4.5 again. You know, I like that. 4.5 is actually a 0, and then 5 is actually a negative 0.002. Negative 0.002. And then this, yeah, no, I'm just not even going to do that last one. Forget it. So this is the hardest one to get. In fact, the wire is getting really hot because of the fact that, you know, you just don't get a strong magnetic field from a single wire. That's why we kept working with the solenoids and the toroids. And so that's really kind of the main point of this lab. But I thought it would be fun to see as much as we can get with this single wire. But we get so overwhelmed, and of course I'm having troubles with getting a good alignment. We should maybe build some extra equipment. But with another set of hands, it's much easier, and you can kind of hold it. But we should make some kind of holding sleeve for this this Hall effect probe. Anyways, let me put these on the board here. So, well, here's what I have for the long straight wire. And so as we move away from the wire, what is the field that we get? And so measuring distance in centimeters, 0.5. 1.0, 1.5, 2.0, 2.5, 3.0, and 3.5, 4.0, and finally 4.5 is my last measurement. And even then, I don't even know if the other two are really accurate, but I do see it dropping off. 0.112 in units of millitesla for the magnetic field, then 0.065, then 0.042, then 0.0 0.030, then 0.021, then 0.015, 0.010, 0.006, 0.005. And so those are the numbers I got. And like I said, that this is probably the hardest one to get anything decent, even harder by yourself. But one more time here, here's what your job is to do. Your fifth and final graph is to plot the magnetic field based upon distance away. Now, remember the equation for the magnetic field from a long straight wire is this equation, okay? And so we'll come back to the theoretical one in a moment. But hopefully when you put in your numbers, you will get something that looks like this hyperbola asymptotically approaching 0. And so just do connect together and you'll see that overall pattern. But also, and I've been doing it in red, so let me continue in red. Make another column, and this one I would say make a calculated column, because we could actually then just put in this one formula here. The current is set at 5 amps, and so put that in. In fact, you could save yourself a little bit of typing space by remembering that this 2 pi would cancel, and you can just put in 2 times 10 to the minus 7, then multiplied by 5, then divided by R. Now be careful, R is in centimeters there, so make sure then that you actually put something like this. Take that column and divide it by, so R divided by 100 would be the formula you would want to put in there. And then likewise, you would also want to put in that times 1,000 in order to get the field in milliteslas. So this is one that I would make a new calculated column, not a manual one, although you can do that and then calculate them all with your calculator and just type them in. But then you're going to have these red ones in here and plot that also. And I have a feeling that it would probably be a little bit stronger than what I got with my little configuration here. And that, again, would be your fifth plot. So here's some good news. Number one, we're done. But number two, then there's no discussion questions. We did a lot of data collection and a lot of tough graphs. These graphs are probably the hardest ones we've done here. And that's why I keep giving you hints about how I would do this graph in graphical analysis. Because getting both plots at the same time. Oh, by the way, I should have pointed out, and you probably figured it out if you've gotten this far, but if you click on what you're plotting here, like so it says B field, and you click on that, you'll get a column, and one of them says more, and if you click on more, you get an option of checking which ones you want plot. So by default, graphical analysis only plots one at a time, and so if you click on it and you change it to the other one, you might be going, wait, I can only get one or the other. But no, you can get both, and you can get an infinite number. Well, I'm sure there's a computer limit, but you can get a lot more than just one if you go to the more option. So click on it and don't select the column you just calculated, go to the more. When you get the more, then you get check boxes, and you can check whichever ones you want to be plotted. And so in this case, all 5 of these graphs, and so I should have said it on the first graph, not here on the last graph, but you could get both of them. So all 5 of them should have the actual data we measured in one color or shade, and the other one is the theoretical one in whatever shade. And some of them you can do a formula, some of you can't real well. All of them, I guess you don't have to have a formula. You could just make a manual input and go to the side and calculate them. So if that's the only way you could get the theoretical one, then do that. But I want you to kind of see and look at the graph, the real data, and then the theoretical data for these 3 objects: the solenoid, the toroid, and the long straight wire. And I guess the only thing we're missing would have been a ring. But this was long enough and I think complete enough. All right, so we're done with this lab, and of course turn it in through Canvas. All right. Talk to you soon.